We're going to take a look at our last chapter for the course, which is chapter 9, and the name of the chapter is Inferring Population Means. So we're using a lot of the same ideas we used in chapter 7 and chapter 8, but instead of talking about proportions and population proportions, we're going to now talk about the means for those populations and what we think the means are based on our samples that we collect. So this first section is a lot of vocabulary and a lot of symbols. Some of this is a review of what we've done before. So our 9.1, the title is Sample Means of Random Samples. So we're interested in looking at the accuracy and precision of the sample mean, as we can use that as an estimate for a population mean and be able to find the standard error for the sampling distribution that comes from taking those sample means. So a couple of notations we learned back in chapter 7. You'll remember that the Greek letter mu, that stood for the population mean. So the mean for the population, which we usually have to estimate based on our sample. So our sample x bar represents our sample mean. So we pull a random sample and we calculate the mean. That sample mean is given by x bar. Sigma, so the lowercase Greek letter sigma, that remember was the population standard deviation, and S was the standard deviation for our sample. So the sample standard deviation is what S stood for, lowercase s. We are interested in looking at 3 general characteristics related to the sample mean. First of all, accuracy. So how accurate is our sample at actually predicting the population mean? We say that the sample mean is unbiased so long as we have a random sample, and we're only going to deal with random samples. That's all we have to worry about. So it's unbiased when estimating the population mean as long as we have a random sample. On average, the sample mean will be the same or close to what we think the population mean will be. Just like it was with p hat and p. We generally thought p hat gave us a good estimate for what p was, the population proportion, as long as we had a random sample. We're also interested in talking about the precision. So remember, accuracy and precision when we're doing samples is really important. The precision, remember, depends on how much variability is there from one sample to the next. The larger the sample sizes that you're pulling, the better your precision. So the more observations that we collect, the more precise the sample becomes. And remember, that lowers our standard error. So this is back from chapter 7. Same thing we talked about earlier. The same rules apply. And then finally, we're interested in looking at the distribution. So remember the sampling distribution. Let's see. I think I'm spelling that wrong. Let me try that again. The distribution. There we go. So the distribution or the sampling distribution. So the sampling distribution can be thought of as the distribution of all the possible sample means that could exist from drawing sample after sample after sample of a certain size from a population. So say we pull samples of size 100, sample, and we calculate their means. We put all those together. That gives us our sampling distribution. So the standard deviation of the sampling distribution, remember the term for that back in chapter 7, that was called the standard error. And we use the standard error in chapter 8 as well in computing our test statistics, but usually we use StatCrunch to help us calculate that. And you'll remember too that as the sample size increases, so larger samples, remember, are always better. As the sample size increases, that causes the standard error to decrease. So standard error decreases, but it doesn't matter what happens with the sample sizes. The mean, the mean will always remain the same. So the mean will remain the same. The mean of the population is what it is. It doesn't matter what the samples say. The mean is what it is. Now we estimate what we think it is, but the mean doesn't change. But the standard error will change when we have larger sample sizes. But the mean will remain the same. All right, so a couple of key points. For all populations, the sample mean, as long as it's based on a random sample, we say that it is unbiased. So it's an unbiased estimator for the population mean. And like I said, we'll always work with random samples, so we don't have to worry about that changing. The standard error for the sample mean, so our formula is a little bit different from what we had in Chapter 7. Our standard error now is going to be calculated by taking sigma and dividing it by the square root of n. So n is still our sample size. So sigma divided by the square root of n. All right, so let's take a look at a couple of examples. A student has a large digital music library. The mean length of songs is 258 seconds with a standard deviation of 87 seconds. The student creates a playlist that contains 30 randomly selected songs. So part A says, is the mean value of 258 seconds a parameter or a statistic? So the same rules apply. Remember, parameters are measurements that are made on the population. Statistics are measurements that's made on the sample. So if the mean length of all songs in his entire collection is 258 seconds, that would be a parameter, right? So the symbol for that, because that's the mean length, the symbol for that would be mu. So mu is equal to 258 seconds, and it would be a parameter because it's a measurement on the population. All right. Okay, part B. What should the student expect on average for the song length to be on the playlist? So he expects the song length to be the same as let me read that question again. What should the student expect the average song length? So we're looking for average. That's another way of asking the mean. So the mean song length to be for the playlist. So since we did a random sample, we can assume that our sample mean length is going to be the same as the population sample mean length. So it can vary, but it should be about the same as the population. So let's write some things down. So we took a random sample, right? It was a randomly selected random sample. So our sample mean should be the same. So X bar should be the same as mu, should be about the same. Okay, so that means we would expect our average song length to be the same, 258 seconds. All right, part C, what is the standard error for the mean song length of 30 randomly selected songs? So that's our new formula, the one we had back here. So let's take a look. So our standard error, we're going to do sigma divided by the square root of n. So our sigma, I believe they gave that to us. Remember, sigma is the standard deviation for the population. So for us, that's going to be 87 seconds. So we're going to do 87 seconds divided by n. Remember, n was our sample size. So since we selected 30 songs, that's going to be the square root of 30. So our standard error is 15.9 seconds. What does that mean? That means one song to the next, the fluctuation we expect to be around 15.9 seconds. Some are higher, some are lower, obviously, but we expect them to fluctuate by about 15.9 seconds. So part D says, would a playlist of 50 songs have a standard error that is greater than or less than your answer to part C? Well, just think mathematically what's happening. If n is larger, what happens then to this fraction as n gets larger? Remember what happens to fractions. If the denominator gets larger, the entire fraction gets smaller. So what should happen? The standard error would be, is greater than or less than. So if the denominator gets larger, the fraction gets smaller. So that means it should be less than. So our standard error would be less than our answer in part C, which was the 15.9 seconds. If you want to actually calculate it, you can go ahead and do that. It would be 87 divided by the square root of 50 this time. So then I'm getting an answer of approximately 12.3 seconds. So you can go ahead and work it out if you want to. I'm using S for seconds, but you don't have to. You should be able to kind of think through that. If the denominator gets bigger, the fraction gets smaller. So the larger the sample size, the smaller your standard error is going to be. That's the point there. Okay, let's do one more. The average income in the District of Columbia in 2013 was $76,000 per person per year. That was larger than the average income for any particular state. Suppose the standard deviation is 35,000 and the distribution is right skewed. Suppose we take random samples of 100 residents from the DC area. What value should we expect for the sample mean and why? So the key word here is random. We're taking random samples. So if we have a random sample, that means our estimator is unbiased. So we can say, let's see, we expect the value or the average value of the salary to be about $76,000. And you can say since we took random samples, we took a random sample, which means we have an unbiased estimator for the mean salary. Okay. All right, and then part B is asking us to compute the standard error again. So if we take a random sample of 100 DC residents, our standard error formula, we're going to do sigma divided by the square root of n. So sigma is the standard deviation for the population, and that would be 35,000 divided by the square root of 100, which of course is a nice number. That would be 10. So we're just going to lose one of the zeros, and we get $3,500. So that means the salary from one person to the next in my sample is going to fluctuate by about $3,500.